The Big Bang was not the beginning. That is a scientific consequence. It is a consequence of 3 different mathematical models that all agree on one thing. Asking what came before is not a stupid question. The standard answer is time began at the Big Bang. That is just a polite way of saying we don't know, and the question is often dismissed. But physicists have been working on real answers. Not 1, 3. These 3 models do not just imagine a before. They make predictions. Predictions we might test. So today we treat this like a detective case. 3 suspects, 3 stories, 1 honest conclusion. First, we have to talk about why the standard answer is so unsatisfying. It all comes down to a frozen pizza. Imagine you pull a frozen pizza out of the freezer. You put it on the counter. It thaws, the cheese gets soft. The pepperoni slides around. Entropy increases. That is the second law of thermodynamics. Things get messier over time. Now imagine playing that video backward. A thawed, messy pizza slowly assembles itself back into a perfect frozen disk. That looks wrong. That looks impossible. The universe has the same problem. We look out into space, and we see the cosmic microwave background. It is the leftover heat from the early universe, and it is incredibly smooth. Almost exactly the same temperature in every direction. That means the early universe was like a perfectly frozen pizza. Low entropy, extremely ordered. But here is the thing. Entropy always increases. So if the universe is getting messier now, it must have been even more ordered in the past. The Big Bang was the most ordered state of all. Why? Why would the universe start in such an unlikely special low-entropy state? The standard answer, the no time before answer, just says it did. Stop asking. That is not an explanation. That's just a way to end the conversation. So physicists built models to explain that weirdness. Suspect number 1. The Carroll-Chen model. Sean Carroll and Jennifer Chen proposed this in 2004. Their idea is wild. There was no beginning. The universe just exists eternally, but not in the way you think. Imagine an infinite cosmic hourglass. In the middle, the glass is pinched very narrow. That narrow point is the Big Bang, but the hourglass is symmetric. It expands in both directions. Sand can flow both ways. In this model, a tiny patch of space spontaneously nucleates. It just pops into existence as a de Sitter space. That is a universe filled with dark energy, expanding exponentially fast. Quantum fluctuations cause some regions to collapse and bounce. Those bounces create hot Big Bangs like ours. But because the space is infinite, this happens over and over in both time directions. From our side, we see a contracting phase that bounces into our expanding phase. An observer on the other side would see the same thing, but their arrow of time points the opposite way. Both observers think they are in the expanding future. Both are right. The model makes a prediction. This eternal inflation would leave specific statistical patterns in the cosmic microwave background. Tiny temperature variations. We could look for those, but there is a catch. It is called the measure problem. In an infinite universe with infinite bounces, every possible outcome happens an infinite number of times. So how do you calculate probabilities? You cannot just count outcomes because infinity divided by infinity is nonsense. The model is mathematically elegant but physically slippery. It's like a census where everyone has infinite clones, probabilities break down. That's the challenge. That is suspect 1. A beautiful hourglass with a counting problem. Suspect number 2 is even weirder. The Barbour-Koslowski-Mercati model. Julian Barbour, Tim Koslowski, and Flavio Mercati published this in 2014 in Physical Review Letters. This is a real peer-reviewed paper. Their idea is that time itself is not fundamental. It is a statistical illusion. They use something called shape dynamics. In normal physics, we care about the size of things. Distance, volume, scale. In shape dynamics, only relative shapes matter. A triangle is a triangle whether it is 1 centimeter wide or 1 kilometer wide. The absolute scale is irrelevant. So what does the universe look like in this picture? It is a collection of shapes evolving through a high-dimensional space. And at one point, the volume of the universe is at a minimum. They call this the Janus point. Janus was the Roman god with two faces looking in opposite directions. At the Janus point, complexity is lowest. Entropy is lowest. It is the most ordered state. As you move away from the Janus point in either direction, volume increases and entropy increases. Complexity emerges. Structure forms. Galaxies, stars, planets, frozen pizzas. Two observers, one on each side of the Janus point, would both see an expanding universe. Both would see an arrow of time pointing away from the minimum. Both would think they are in the future. Both would be right. Time is just a measure of how far you are from that central point of maximal simplicity. It emerges from gravitational chaos. The model makes a prediction too. It produces a specific power spectrum of density fluctuations. That is the pattern of how lumpy the universe is. We can compare that to data from the Planck satellite. So far, it is not ruled out, but the model has a problem. It is not clear how to connect it to standard quantum field theory. It's like a beautiful engine with no transmission to the rest of physics. Still, it is a serious mathematical proposal. Time as a side effect of shape. Suspect number 3 is the honest one, the past hypothesis. This comes from philosopher David Albert and his 2000 book Time and Chance. The idea is brutally simple. The universe started in an extremely low entropy state. That is it. No bounce. No eternal inflation. No shape dynamics, just a brute fact. A law-like initial condition. You do not ask why the speed of light is constant. You just accept it. Albert says you should accept the low entropy start the same way. It is the boundary condition that makes everything else work. The arrow of time, the second law, the existence of structure, the fact that you can remember the past but not the future. All of it flows from that one weird initial state. Think of it like this. You open a freezer and find a perfectly frozen pizza. You did not see who put it there. You do not know how it was made. You just know it is frozen. The past hypothesis says stop looking for the delivery guy. The frozen pizza is just a fact about the universe. This is consistent with all observations. It requires no new physics. It is minimal. It is also deeply unsatisfying. It feels like giving up. It explains nothing. It just relabels the mystery. But here is the uncomfortable truth. It might be correct. The universe might just be like that. We put a low entropy stamp on the beginning and call it a day. That is the honest, unglamorous answer. The one that says we do not know and maybe we cannot know. So which one is right? Can we even test them? This is where we hit the Planck wall. The Planck time is about 5.4 times 10 to the negative 44 seconds after the Big Bang. Before that, our physics breaks. General relativity and quantum mechanics stop playing nice. We have no working theory of quantum gravity, so we cannot see past that moment directly. It is a glowing barrier with equations scribbled on it. But there is hope. The early universe may have left fingerprints. The cosmic microwave background is like a crime scene photo taken 380,000 years after the event. It does not show the Big Bang itself, but it shows the imprint of processes that happened much earlier. Inflation, bounces, shape dynamics. They all predict slightly different patterns in that ancient light. Gravitational waves could also carry signals from the Planck epoch. Missions like BICEP and the Simons Observatory are looking for those right now. The problem is all three models are mathematically self-consistent. They are rigorous. They are serious, but none is currently testable in a unique way. They might all be wrong. They might be different perspectives on the same underlying physics. We are detectives with 3 suspects and no clear evidence. The honest answer is we do not know. But we have real leads. That is actually more interesting than the fake smart answer. The no time before dodge is just intellectual laziness dressed up as profundity. These 3 models show that asking what came before is a legitimate scientific question. The Carroll-Chen model gives us a symmetric eternal hourglass. The Barbour model gives us time as a statistical ghost emerging from shape. The past hypothesis gives us a frozen pizza and a simple acceptance. Each one teaches us something. Each one forces us to think carefully about what time even is. So here is your mental toolkit. Next time someone says time began at the Big Bang, you can say sure, but which Big Bang? The one that is a bounce, the one that is a midpoint, or the one that is just a brute fact? The question is not stupid. The answers are not complete, but they exist. We are still trying to decipher the universe's recipe. The universe might be an hourglass, a Janus coin, or a locked freezer. We are prying it open one cosmic microwave photon at a time. And that is where we are. 3 models, 1 honest conclusion, and a frozen pizza that started it all.